Chapter 19. The hydrogen atom and hydrogenic ions. Section 19.1. The Schrödinger equation of the hydrogen atom. In the hydrogen atom, there's one proton and one electron. The energy of the electron is the sum of its kinetic energy and the attraction it feels from the proton. In general, the interaction between two charges Q1 and Q2 is Q1 times Q2 over 4 pi epsilon r. R is the distance between the two charges. Therefore, the attraction the electron feels from the proton in the hydrogen atom is negative E squared over 4 pi epsilon r. We have a negative sign here because the charges of the proton and the electron are opposite to each other. R is the distance between the electron and the proton. R is the magnitude of this vector. The physical constant epsilon 0 is the vacuum permittivity or permittivity of free space over here. Epsilon 0 is 8.85 times 10 to the power of negative 12 farads per meter. The unit farad is the SI-derived unit of electrical capacitance, and each farad is equal to 1 ampere second over volt, or 1 coulomb over volt, or 1 joule over volt squared, or coulomb squared over joule. 1 joule is equal to 1 coulomb times 1 volt. Now the Coulomb constant is defined to be 1 over 4 pi epsilon 0, which is roughly 9 times 10 to the power of 9 joule meter per coulomb squared. So if you have a coulomb charges over here, another coulomb charges 1 meter away, well, the potential energy between this two coulomb charges, 1 coulomb on each side, is roughly 9 times 10 to the power of 9 joule. The kinetic energy operator of the electron is written as negative h bar squared over 2me times the Laplacian operator. The Laplacian operator is the second derivatives with respect to x, y, and z direction for a three-dimensional system. When we have a one-dimensional system, the Laplacian is simply delta squared over delta x squared. Now let's look at the three-dimensional system. We can use x, y, and z to specify the location or position of the electron. For example, here, assuming the center is the proton. But also, we can use the r, theta, and phi polar spherical coordinates to specify the position of the electron relative to the center, which is the proton. In this case, z is r times cosine theta, and x is r sine theta cosine phi, y is r sine theta sine phi. Also, we can express r, phi, and theta in terms of x, y, and z. R is the square root of x squared plus y squared plus z squared. Tangent phi is y over x. Tangent theta is the square root of x squared plus y squared over z. R is from 0 to infinity. Theta is between 0 and pi. Theta corresponds to the latitude of Earth. Phi can be from 0 to 2 pi. Phi corresponds to the longitude of Earth. In Cartesian coordinates, we have the Laplacian equals delta squared over delta x squared plus delta squared over delta y squared plus delta squared over delta z squared. However, if we simply use the Cartesian coordinates to solve the Schrödinger equation for the hydrogen atom, we'll get nowhere. We have to resort to the spherical polar coordinates. In spherical polar coordinates, we have the Laplacian expressed as this: 1 over r squared times the sum of the three terms. The first term is delta over delta r of r squared delta delta r. The second term is 1 over sine theta delta over delta theta of sine theta times delta over delta theta. The last one is 1 over sine theta squared delta squared over delta phi squared. It looks more complicated, but we have to use the Laplacian in spherical polar coordinates to solve the Schrödinger equation for the hydrogen atom. We can see the derivation from the Laplacian in Cartesian coordinates to the Laplacian in spherical polar coordinates in Appendix B. The kinetic energy of the nucleus is much smaller than that of the electron. This is because the total momentum of the two interacting particles, including the electron and the nucleus, must be conserved when there is no external force. So when we study just the hydrogen atom, well, the center of mass of the hydrogen atom is stationary, and we have me times ve equals mp times vp with the negative sign here. So over here we have the momentum of the electron. Over here we have the momentum of the proton. They should be opposite to each other. We can square both sides. We get me ve squared equals mp vp squared. And now, because the mass of a proton is 1800 times that of the electron, we have this equation. So me ve squared over 2me is about 1800 times mp vp squared over 2mp. Now look, me ve squared equals mp vp squared. And over here we have the kinetic energy of the electron. Over here we have the kinetic energy of the proton. So now you can see from this equation, the kinetic energy of the electron is 1800 times the kinetic energy of the proton. Therefore, the kinetic energy of the nucleus, in this case for the hydrogen atom, it's a proton, can be neglected only because the kinetic energy of the nucleus is always much smaller than the kinetic energy of the electrons. Now the Schrödinger equation can be approximated to include only the kinetic energy of the electron here and the attraction, the electron fields. The kinetic energy operator is negative h bar squared over 2me times Laplacian. The potential energy is the attraction, the electron fields from the proton, which is negative e squared over 4 pi epsilon 0 times r. And we apply this Hamiltonian to psi, h psi equals e psi. This Laplacian in Cartesian coordinates is the sum of the 3 second derivatives with respect to x, y, and z, but in polar spherical coordinates, the Laplacian is more complex. It's 1 over r squared, and then delta over delta r squared, delta over delta r, plus the second term, 1 over sine theta, delta over delta theta, sine theta times delta over delta theta plus 1 over sine theta squared, delta squared over delta phi squared. The derivation from the Cartesian coordinates to the polar coordinates can be found in Appendix P. X is r times sine theta times cosine phi. Y is r times sine theta times sine phi. And z is r times cosine theta.